So we're here. I think I've got stuff ready. Hopefully we don't have technical issues today. We had some problems yesterday. Get this right. So I think there are 18 of you. It's not a huge crowd when we've got 45 in the class, but it's actually better than the other two classes yesterday where I'm going to get myself started. Can people hear me and see my screen? Someone just confirm, that would be appreciated. Good. Excellent. Thank you very much. Good morning, everyone. And it is start time. So this morning, it's really dreary outdoors. I didn't take any pictures. But and last week was pretty dreary as well. But Friday morning was really nice. And we were up early as usual. And this is the Northwest Arm. There's Dora, of course. I know it all looks dark. It was actually a little bit lighter than the picture shows, but I just don't know how to adjust lighting on my phone. My phone is an old one, so it probably doesn't allow it. For those of you unfamiliar with the Northwest Arm, it parallels the Halifax Harbor. It's sort of like a back harbor, and around the south end. Point Pleasant Park is at the end of it. That in the middle is Dalhousie. That's an apartment building at the bottom of Coburg Road and Oxford Street, I think. St. Mary's is just beyond there. I can't quite. Normally, I can get the Loyola building in a shot, but it doesn't seem to be there. And that's the Dingle Tower. If you've been down Purcell's Cove Road. Anyway, it's a nice spot to go in the morning, and it's not a long walk from my house. And this week, well, Friday afternoon, drove down to Kingsburg. That's where I'm staying for the next week or two. And this is on the weekend, again, around sunrise. And we had a hurricane pass by well to the south of us, Hurricane Epsilon, but it created a lot of storm surge, a lot of high waves. You didn't see wind or rain or anything up here, but the waves were quite large. And so this was Hell Point, which is at the entrance to the Kings Bay, and the breakers out here were huge. That it's, I think it's called Hell Point because it's got a lot of shoals out around it. It's a dangerous point to go around. Anyway, on with the show. Picture show's over. A variety of updates. Test number 3, grades were awful. That's not your fault. I know the scatter chart correlation, that was too difficult. I'm revising the way it's being graded, and I'm reviewing other questions to see how to change the grading on them and make some type of adjustment. I've got some flexibility in being able to allow multiple right answers, but some of the right answers weren't right, or some of the ones I might mark. I've got to go through this further and get the class average up where it should be. Assignment 3 has been posted. It's due this Friday. It's all on multiple regression, primarily not material today, but the material we did in the 2 classes last week is where you should focus on in doing that assignment. And you'll find, like the example we'll do today, with each question, I'd copy the data into a new sheet, do the question, and so on, and that way you can keep your data organized, because of restrictions in Excel with the way it does plots, the way it does correlation, regression, and having columns in a certain order or grouped together, that you're going to find it's easier for each question. Just copy what you need into a new sheet, organize it the way you want it, and then do it. I'm trying to think. If you've got other questions on assignment 3, I've had quite a few already. Please send me an email. Some are just having trouble getting started with it, and I think once they get started, they'll be fine. So we've been looking at building models and issues associated with improving those sorts of models. The first one we built looked like it was a good model. It had an R-square of 0.75, 75%, which is actually quite good. But the standard error was $232. So it meant predictions could easily be off by $400, which isn't very good. So if you're going to improve, then you've got to add something new, and that's generally new information. And that we looked at limit as something to add. It didn't help. It had no new information. It had the same information as rating did. We tried adding income, and we found out that income and rating are linked together. They're correlated very, very strongly with each other. And so it was then we couldn't talk about the effect of income without talking about the effect of rating, because as soon as you change the income, you change the rating. You can't change one without the other. This is a very big challenge, but it's one that is very, very common to a huge number of situations. And sometimes you can make some accommodation, but often it's very difficult. That generally, when we're building a model, I like to build it in steps. It's just the way I do problem solving. I try to break it into small steps and go through each one. Doing it all at once is overwhelming at times, and it helps me understand what's happening. To improve it, though, the approach I'm suggesting to you is basically learn from your mistakes. An old expression that your mistakes are the errors you're making in predictions. So find out where the errors are and see if there's some cause for those errors. Can you study the errors and find a pattern? If you have a pattern, that means you can exploit it and do better. So the errors are called residuals, and it's not a word we use all the time. Residual means what's left over. So what we do is we study the residuals, find something, try to pick, if you have choices, pick the best one you can, and implement it, and then go back through again, study that. And it's this cyclical fashion of it's the whole idea of continuous improvement even goes through this sort of thing. Study where you can improve, implement something, see what the outcome is, and then go back and try to do it again. Oh, are we stuck on our slides again? This is what happened to me yesterday with both classes. Oops, I can go backwards, but it won't let me go forward. So I'm ready for this. I've got my slides here. So let me go back. I've got to figure out what is causing this problem. So this is what we had. I know it's a little bit smaller putting it this way, but hopefully that works. And so let's go to the next one here, because I'm just afraid. I wonder if I present. That'll take up my whole screen probably. Yeah, it does. Okay, we'll do it this way. So we did that. Okay. So what I want to do today is continue that exploration of residuals. What other things can we learn from it? And I'm going to look at, instead of adding new variables, because probably age or education isn't going to be that helpful anyway, to look at other aspects of the problem. And one thing is whether or not it's a linear model. A linear model means everything is a straight line. So it's a straight line relationship with income. It's a straight line relationship with rating. Actually, it goes down with income, it goes up with rating. But these are linear. And if you did quant one here, all you did was linear models. When you think of cost functions, where even if it was costs for 3 different products, it may be 3 times number of units of A plus 5 times number of units of B plus 7 times number of units of C. Those are linear models. You're adding up different terms, and each one is a number times a variable, number times a variable. Really nice, easy to work with. And we're trying to stick with that. But what if it's a curve? What if it doesn't go up as a straight line? What if it's a wavy line? And we got to look at that. And how can we tell if it is? Another thing, we've been looking at the correlation with quantitative variables. And as I said, I don't think age is going to help me much, or number of years of education or number of credit cards. But we've got nominal variables as well. We've got gender, we've got marital status, whether you're a student, what your ethnicity is, or at least are you Caucasian, African American, or Asian, into those big type blocks. That how do I use that information? Because it's not stuff I would throw and get an easy correlation coefficient. And even if I found it was useful, how do I include words in a formula? So we'll look at those. And I'll just summarize the various issues we've looked at. And let me get down. Where's the next one? Okay, so I'm going back and looking at residuals. So let's go back to the beginning of our examination of residuals. We fit a simple model last Tuesday, I think it was, and it just had rating and it had balance. And last class said, well, where isn't it working well? Where am I getting bad predictions? So the residuals were the difference between the prediction and what actually happened. And we could get that. We could request a plot and a list of all those residuals when we do an analysis, when we fit a model. And we'll show examples of that as we go today. And the only pattern we noted was this line that was over here. And that's because you couldn't have a balance that was less than 0. And so what could we do to improve things? We suggested, can I go ahead? Let's go. Yep. We thought, well, if we knew who had a balance of 0, maybe we could fix the pattern. So we could maybe create 2 models, a classification model that said who doesn't owe anything and who does. And well, those that don't own anything, we know their balance at 0. And those that do owe us something, how big is their balance? Okay, and so we could measure those sort of like in Target, it had 2 models. One is who is pregnant, pregnant, not pregnant, and then those who were pregnant, what's your due date? Because those who weren't pregnant didn't have a due date. Similar sort of situation. So that would be a different approach we could take on this, but we're not going to. We're going to stick with these regression ones. Classification's the next topic. So last day, I fit a model that had income and rating in it. So how did that change things? So let me just show you what happens. Let me go back. As you can see, I've got a spreadsheet. This one I'll make, I don't think I've made it visible to you. So I'll, the last day we took, I'll make the spreadsheet so you can download and play with it if you'd like. That last day we took income, rating, balance, and from that we fit a regression model. It had this output, okay? And I could have asked for what was the residuals there. So I could have had, this is the same output again with, oops, sorry, this is the rating residual. So what I did was when I requested this regression, I requested it produce these. And this is the one with both income and rating. Just to go back, I can do this again and I'll just show you. Never hurts to show you a few extra times. So with this one here, this is the stuff from the end of last class. I could go up to data. I can go to data analysis. I'm looking at regression analysis. And I'm trying to predict. That's my Y is what I'm trying to predict. And so that's in column C1 up to C401. And my X variables, there's already stuff here. Every time you use regression, it tends to remember what the last problem was. And this was actually carry over from a different data set. It's the data set in your assignment. The X's are in columns A and B from row 1 down to row 401. I've got labels. I'm going to put my output right here in E1. So I've got it on the same page, and you'll see I'm going to do this regularly today. I put it all on the one page, and I've checked off residuals and residual plots. Give that to me. So this is how I produce all that stuff. There it comes. Okay, so here was this model and how it performed, and these were the coefficients, and I'm going to work with those in just a minute. And over here on the right, it gives me plots, and so it gave me two because I got two variables now. I got rating and I've got income. And so here's the plot for rating. Here's the plot for income. And with rating, we're going to look at this in a minute. It looks like there's some odd things going on here. And with income, it might as well. Okay. And again, where these come from. Here were all these balances, 33, 903, and so on. And Excel took its model and made predictions. So the first one, where it says 333, the predicted value was 468. That's too big. It's over by 135. So if I take 333 from 468, I get the minus 135. And so each of these are the predicted values for the balances that I've got over here. Okay? And the difference, it really doesn't matter if you took the actual minus predicted or predicted minus actual. It's just the mirror image of one another. And you get that, this one I was too high by 135. This one I'm too low by 343, and so on down. Okay? So that's the stuff that's plotted in those plots. Let me get back to my slides. So here was the rating one. It's a little bit bigger than I had in my regression there. And if you look at it, there seem to be patterns to it. Okay, but let me show you what it was before, what it is now. I'm just putting them side by side. So this is the one we had before with this sloping line down the side, and otherwise it was just noise up and down. Now that I've got income in here, then what's left over has a different pattern. It's not as spread out. Notice this one went up to 800, down to almost minus 800. Now it's more from minus 300 to plus 600. So it's reduced the size of the errors. Now it's the standard error shrank. So they're a little bit tighter, and it's got still this sloping sort of edge here, like it did before, though it's a little more blurry at the moment. But look at the way it goes down sharply, and then it turns and goes back up again. I guess that's here. Went down, turned up. But it had this scatter above it before. That scatter seems to be moved over. So it's different. So I've got a U shape here, but even that U turns and flattens out here. So I go down, up, then maybe down again. So I got a curve here with rating. I should have an even scatter. And then I've got this cloud up here, which I've got two things going on. I can only deal with one thing at a time. I'll get to that there. And what happens with income? Remember, it's got its scatter. And this one, it's not too bad. Ideally, we want a scatter. Oh, I can write on my slides here. That would look like this sort of thing. Like it would have a band, like this sort of thing. Or it would look like it was in a box. Yeah, let me draw it as a box. Maybe something like this. So that would be the way my scatter would look. It would just be even right across. Okay. But it's not. It's got a bunch that are floating way up here. And even the ones down here seem to be more clustered below than they are above. it's not even balanced. This line I drew at minus 250, this one at plus 250. And you see I've got all these ones up above it. So something's going on. And but let's deal with rating first and one issue at a time here. So let me go back here and we'll go back to the beginning with rating and see if we could have foreseen the problem that we've got. That if you look at it, it almost looks like an S. It goes flat here, goes up like that, and then curves off this way. So it's got a squiggly type of line here. And it didn't really come up in our residual plot before that it was curvy like that, but it has now. It was probably because this scatter in here, this cloud up above, having both happen at the same time made it hard to see. But now I can see there are two things here, and this one is curved. So how will I deal with it as a curve in my model? So curves, um, I, I don't know. You probably view math formulas as all being alike, but they're just all ugly math. But there's some that are really nice and easy to work with, and some that are not. The nice, easy guys are straight lines. They're really easy to do all kinds of things with. But when you get, and even if you had a couple of points and you were trying to draw a line between them, if you drew a straight line, there's only one straight line. There's one line that connects 2 points together. But if I have a curve and I got 2 points, there are all kinds of curves. They can go all over the place. Even if I had 100 points and I wanted to put a curve through it, I can put any number of curves because I'm only going to see a curve over the range that I got. So let me go back and look at this. See this guy? It goes with ratings from 0 up to 1,000. We never care about what happens with more than 1,000 or less than 0. And so I could find a curve that goes down, goes up, and then goes flat like that. That seems to be the pattern I've got here. What does it do afterwards? Does it go down? Does it turn around and go back up again? Over here, when it went negative, would it go down? Would it turn up? Would it go up forever? All of those are different possibilities. So those are different formulas that fit those. So they may all behave the same way over a narrow band, but they may be all kinds of different formulas and lots of ugly formulas. If you recall formulas in finance for working out how big a mortgage you can take out or how big a car loan you can get, you had exponents up there and fractions and numbers all over the place. Those are messy formulas. If you had logarithms and sines and cosines and exponentials. So there's lots of different types of formulas you can have. And they're challenging to work with. Straight lines that were nice. Well, a close relative to a straight line is a polynomial. A polynomial has a number times a variable plus number times a variable plus number times a variable like a linear function does. But those variables could be squares or cubes or just linear terms or constant terms. So it's taking one variable and creating a formula that recycles that variable in different ways. So here's my straight line portion, but then I'll add one curve to it. A square goes U-shaped or as a dome shape, and that's what a square will add to my formula. If I add a cube to my formula, then it can go up and then down and up again. It can change direction twice. So it changes once, changes twice, or even it changes its rate at which it's moving in different sorts of ways so that it may still keep going up, but it has curvature, dome-shaped curvature, and cup-shaped curvature in it if you've got a cube function. So this is probably the simplest one where I can get my extra terms in it. And that's what I'm going to use. That we've already got a constant term. We've already got a linear term. So it's just adding rating squared, rating cubed. But rating can go up to 1,000. 1,000 squared is 1,000,000. Okay, so I can get values of something times a number that's up to 1,000,000. So I'd have a coefficient times a variable that might be 300,000. So that's a big number. And then rating cubed is 1,000,000,000. So I could have a coefficient in my model, if I went back to that model that I had here, A times 37 million or 942 million. It's a big, 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 big number. And so if I got a huge number here, and since I got balances that are relatively small, A is a really, really tiny number. And even B will probably be a tiny, tiny number. And by tiny, I mean 0.0000003 something. Very small. I don't like those. I don't like a whole string of zeros. I like my numbers to be manageable size, not too big, not too small. So one way of doing that type of thing, of keeping your numbers the size that are not too big, not too small, is to scale them. And the most common scaling method is creating z-scores. A z-score is just take the rating, subtract off the mean rating. Mean is around 350. So if my score was 600, I'd subtract off 350 and get a gap of 250. So it's 250 points above the average. Is that big? Well, a way of adjusting for how big it is divide by the standard deviation, which is 150. And I'd end up getting a z-score of around 1.6, 1.7. So it's a manageable number. And if I squared it, I'd get a number, I don't know, around 2 or something like that, or 2.5. That if I cubed it, maybe it gets up to 3 or 4. But it's not huge. Okay, it'll keep all the numbers relatively small. And z-scores most of the time are between -2 and +2. With outliers, we sometimes get up to 4 or -7 or -10. But that's only if you have some extreme values. If your data is not too messy, then you'll find that the z-scores stay relatively modest in size. But even if they got up to 10, squaring that's 100. It's not too bad. So I created a spreadsheet with these new things in it. So let me go and show you the actual sheet. So this is my rating cubed. I took my income column, my rating column. I created a new thing called ZRAT, which was the z-score. And then I created a column that squared it, took the -0.46 and squared it. And then another column that took the -0.46 and cubed it. So this one is a positive, that's a negative because of cubing the negatives. And I've still got balance. So I could fit a new model with this set of variables in it to predict balance. Okay? And that's what I did. And so just to show you how I did it again, I went to data analysis. I picked regression. This time my balance, it's in column E. And my variables are from columns A to column D now. I've kept everything on the same sheet. I've got labels. I kept them on the same sheet. I could put it in column H. Okay? And I asked for residuals and residual plots. So we asked for all of those things. And this is the result that I got. Okay? So, and it might be easier to evaluate this in the context of what we've already done. So let me get back to my slides. So this is what I did, was I used this stuff. And this is at least a useful portion of the output. Remember, we don't bother with this ANOVA table. That this tells me about how good the model is, and this tells me what the model looks like. So let me go, whoops, here we are. I want to look at the old model and the new model. My old model had an R-square of 0.875. I know I don't like the number or using R-square, but it's one measure of performance. So to get better, it means I want to get towards 100%. I'm at 87.5%. And I get up to 0.894. So it's about 2% better, not very much. That it's not a huge improvement. If I look at the standard error, before it was $163, so my forecasts were easily off by $163, possibly more. Now they're off by $150. Better, but not an awful lot. Not a huge improvement. That if I look at my model, the numbers have all changed. Okay? That my intercept is not something I can explain anyway. It's just a number I need in my formula, because the intercept is when all your X variables are zero. So the balance of someone that has no income and no credit. We don't have such a person. So this is like outside of my graph. That's something I'd never see. The income, we were saying before, as income went up, balance went down, but that was because rating also goes up. So it was confusing. It went from -7 to -9. Okay, similar size. And the coefficient for rating by itself went from about 4 up to 4.3. So it's a little bit bigger. But then I've got these other guys times my z-scores, z squared and z cubed. These are the ones that I scaled. The numbers they look big, but that doesn't mean they're important, because remember, the z values, even squared or cubed, are quite small. Okay, so this doesn't have necessarily a huge impact of moving things up or down. It's just a formula now. So looking at it, I've still got this multicollinearity problem that between income and rating, so that I can't separate them. And so trying to explain this model is still a mess. The multicollinearity problem stays even with a nonlinear model. It's not surprising. Um, so this is a problem, at least with those two variables, I'm probably not going to be able to resolve. It wasn't because rating was curved. So my model wasn't that much better by those measures, but let's look at the residuals again. And that this was with rating. This was before I made it a curve, and this is after. Well, it still looks like there's a bit of a curve here. Maybe not as much as there, but it's still there. Okay, and the size of my errors looks about the same size, roughly, as I had before. And my standard error, as I said, didn't change much. We've still got the cloud. So it seems I can't fix the curve easily, and I'm not getting a lot of improvement with what I've done already. So let's leave that and go and look at the cloud. What's causing this cloud up here? It's like I have two groups. I have customers, which are in this band, bottom, and then I have these customers out here that are just so different from everybody that having that many outliers suggests there's probably a reason for it. So what I could do is look at my qualitative variables, the ones that were categorical, males and females, married, yes or no, student, yes or no, or ethnicity, it was Caucasian, African American, or Asian. So 3 of those are simple. They're just yes, no, sort of binary. The third one has 3 different values. That one's a little more complicated to model, but it's not any more complicated to examine. So I'm going to look at my residuals once again, but I'm going to look at the residuals with respect to these variables here. So if you remember last class, we did, when looking at residuals and adding a variable, and we had income and rating. What I had done in picking that, I think when, nope, where I am, residual and, oh, this was afterwards. Let me just go back. Do I have it up here? Nope. Rating, residual. Okay. No, I didn't put it in here. But one of the things we were doing before when looking for things to help us predict our residuals was look at the correlation between the residuals and other variables. And this one here was after putting income in and rating in, what was the residual and how did it correlate with the other variables. And that was the way we made our selection. But I've got categorical variables now. How do I look at the relationship between the categorical variables and the residuals? Well, we've done that sort of before. That I could go and think about the different groups and what patterns I'd see. That should I expect a difference between students and non-students with respect to residuals? I know they're different because they probably have lower income and lower ratings, but we've already taken account of those. That should I expect differences between males and females or a pattern that way, married and single, that type of thing. That when we were comparing two groups, we did that before with things like pivot tables and looked at averages. But suppose I don't look at averages, but I look at those qualitative characteristics. And I use something like a box and whisker chart. So what I did was, where's that spreadsheet? You can see I've got lots and lots and lots of tabs here because every time I tried something different, I created a new tab. Oops, I'm moving the wrong way. So I fit this model here that I just talked about with the cubes and all that stuff. And I got residuals. These were all my residuals. I copied these three columns and I pasted them into a new sheet. I pasted them in right over here. And then I went back to my original data set and I took the columns for gender, student, married, and ethnicity, and I pasted them in beside. Okay, so that's what I want to look at. I want to look at this column compared to those variables. And the way I do it was box and whiskers. So I start out, I take this column of residuals without the label. Don't include the label. I go up to insert. I go to recommended chart. It says, just give me a scatter chart. I don't want a scatter chart at the moment. I want a box and whisker chart. And I click OK. And here it is, sitting way down here at the bottom. Okay. That now with this chart, it shows here's most of my data, and then here's my cloud. So if you looked at my residual plot that I had before, that's like this being the box in my box and whisker, and this being the outliers that are up above. But instead of them being spread out across this way, I squished them all together and just showed where's the main bunch and where's the outliers. Okay, so this is the main bunch. Most of the residuals are between minus 200 and about plus 200. And then I've got these odd ones that are up above that I'd like to understand. So To understand it, I could go to select data. And so this is the residual data. Here I'm going to go and edit for the horizontal, and it asks for axis label. So I'm going to start out with this and pick gender. And so I'm going to go all the way down, selecting gender, make sure you don't include the label. Oh dear. I'm not sure if I'm getting all the way down or not because this chart's in my way. I hope I'm fine. Yeah, I'm down to 401. And I click OK. Okay, you can see it's already did that in my chart. And so I got male, female, and look at them. In both cases, the bulk of the data is that clustered in this band here. There's not much difference between these two. And then here are the outliers. So it seems the outliers occur with both males and females. They're both, so both of those groups have this problem with outliers. And the ones that aren't outliers are all clustered together. So I could do this with each of my variables. I could make up charts, and I did that. And I'll show you what they look like. So this was the one with gender. I got that. And then I looked at, are they married? Got the same, almost the same chart. So it doesn't look like being married really matters. If I looked at ethnicity, no, okay, there's a little bit of narrowing, but it's not significant. These really look pretty much the same, and they still got outliers. Everybody's got outliers. I got outliers for marital status. I've got outliers among gender. I've got outliers among the ethnicity. They're all the same. This is not telling me anything. So, of course, I've got the big surprise at the end. If I look at student, my problem solved. These are the ones that aren't students. This is basically all those people that are in the band that I've been twisting around. This is my outliers plus a few more. So all the outliers are students. And then there are a few students that are overlapped in a sense with the main group. But there's two groups here, clearly two groups. So I should try to, in my model, differentiate between students and not students. How do I do that? So I've showed you how I built my chart and how I did all that stuff. So I've got that still in the slides if you want to go back and review it, because it's easy to forget how you do these box and whisker charts. So now I want to use student in my formula. So I've got a formula now that looks sort of big. I've got intercept, I've got income, I've got rating squared, rating cubed, and now I'm going to have student. But student is a word. I can't just put student, not student. But this is, if you did Quant 1, it was probably your last lecture, that they introduced binary variables and yes, no variables. Did you do something or not do it? Yes or no. And a binary variable takes on values of 0 for no and 1 for yes, or the reverse, doesn't matter, as long as you know what's what. So I could have my new variable, student 01, being 1 if the person is a student, and 0 if they're not a student. And you can think about, well, what happens in that model? If the person is not a student, this term here would become 0. So if you're not a student, that's gone. I lose that term altogether. So it's the model that I had previously, sort of, but without the cloud, without the outliers. And we'll see that the numbers change a little bit. But if you are a student, I'm going to get this term in here, and this portion of it is going to equal 1. So this term beta 4 represents the impact of being a student. Being a student, what happens if you're a student? Well, we'll see. So what I did is I recoded my data in this fashion, the way I just described it to you. So I've got income, rating, rating squared, rating cubed, and the student information, I put in a formula, just an if formula. If this is yes, give me a 1. If it's not a yes, then give me a 0. Okay. Um, if you've got blanks, it's not going to like it. Actually, regression does not work with missing values. We can never have missing values and do regression analysis. Should have raised that issue before. Maybe I did. But yeah, regression analysis, the formulas, if you've got blanks, you'll find that it just doesn't work. So anyway, I took my numbers, put them in there, and made this 0, 1. And then let me go back to my spreadsheet. There it is. So I put student in there, did all that 0, 1 stuff. I fit my model, and I got my output from it. Okay. And rather than look at this output, let me go and look at just the main highlights. So here's my model. I've gone, and the first thing I look at generally is R square, just as a quick look. Before, I said I explained 89% of the variation. Now I'm up to 97%, 96, 97%. I've gone up by 7 or 8 percentage points. May not sound much, but remember the best model is 100%. So R squared can't exceed 1. So at this point, I was 11% away from perfect. Now I'm 3% away from perfect. That's a big improvement. And so that is a big jump. And we see it down here at the standard error. Standard error before was $150. Now it's $83. I've cut it almost in half. That's a huge improvement in terms of slicing my errors down by a large amount. So yeah, we've had a big improvement by taking out the cloud, that they were causing all kinds of problems. If you look at the model, did it change much? You'll see it didn't really. So by taking the cloud away and then refitting the model over that tight band, that large group of people that were not students, I just sort of refined my numbers a little bit, but I didn't change them an awful lot. That they, which is good. Generally, I don't like to see a huge change in my coefficients because it suggests, oh, there's something going on, like we had with multiclinearity. That this doesn't seem, its student didn't seem to affect the non-students, okay, the model for them significantly. So that's reassuring. What does this number mean? 417. It suggests that on average, students carry a balance that's $417 higher than a similar person that isn't a student. So if I had two groups of individuals, two large groups, that in one group they all had basically the same rating, same income. Among the students, they have the same rating, same income. So the two groups look the same with respect to income and rating, except one group of students, the other group are not students. And I look at the average balance of the two of them. The average for the student group is $417 higher. So even adjusting for other factors about the individual, students borrow more. So I can't say students borrow more because of their income or because of credit ratings or something else. They just borrow more because of being students and maybe the demands that a student places upon them. This is the average. So there are no doubt some students that would borrow more, borrow less. Again, our predictions, as I said before, are off by $82. But if I'm just looking at the impact on the average student, I think it's 417. It's not perfect. it may not be exactly 417. I shouldn't commit to a specific number, but I think I've measured it reasonably carefully on average, what the average impact is. Again, I keep emphasizing that average because these coefficients reflect average impact, not how it affects one particular person. That if someone challenged me on the 417, they thought, come on, it's not that high. I could look at my standard error, which is about $14. So I said, I could be off by one or even two standard errors. Maybe it's as low as $390. Maybe it's as high, on the other hand, as, I don't know, maybe 440, 450. So maybe between $390 and $450. Whichever way you look at it, it's still a substantial amount of money, particularly compared to the balances we're seeing. Remember, we're looking at balances generally between 0 and maybe $2,000. So saying one group carries a balance that's $400 higher than the other group, that's a big number in this particular thing. So again, standard error gives me an idea of how accurate my coefficients are because they're just estimates. I can go back and look at performance of my model. Here's my income plot. Now that looks the way it should, as just an even sort of box. It's got 4 or 5 numbers down here that might be a problem. If I look at the ratings, I still think there might be some curves in there. Maybe I should use rating to the power of 4. I don't know, but I'm probably not going to improve it dramatically. I don't think. And it's still got these 5 sitting way down here. With the students seem to have a bunch of low values. This is low income, low rating. Those are probably students. So there may be a group of students that this model isn't fitting well. They seem to be a group of students that didn't borrow a lot of money. They've got low incomes, low ratings, they're students, but they didn't borrow like the other ones did. So there may be something I could learn by studying them, but I'm probably not going to make my model that much better now. It's as good as I'm going to get it. So, as I said, highlights of this, R-square is very high in practice. Be skeptical if you see an R-square this high, honestly. It's a great result, that, but it rarely happens we get such good results. So I always get suspicious. I think there's some cheating going on. This is when I started suspecting my data was not real data. They had modified it in some fashion. And it turns out that's the case. It's not real data. That it's hard to make really good predictions of anything. Our standard error is down to $83, which suggests any prediction we make shouldn't be off by more than about $150. So our predictions are not that bad. Remember, we started with a standard error of $232. So it's now about a third of what we started with. So we've had some significant improvement. It's not perfect, but it's better than what we had at the beginning. Our residual plots are looking reasonably good. Maybe I should investigate those 5. And the main causal thing I've been able to pull out is the impact of being a student. That the impact of rating and income, unfortunately, I can't get into and analyze properly because they're too linked together. But student seems to be separate issue. And so I can talk about that from a causal perspective. So I think been reasonably successful in our model. And as I said, remember our coefficients are estimates. There's a margin for error. So if you're going to get into that causal analysis, take into account that margin for error. And it's not exact, but it does seem to be a separate effect. Remember what standard errors of coefficients mean. It's how accurately you've estimated it. That that, and this one is interesting to go and look at. If you go back and look at standard error, often people don't look at this column. They look at these summary measures up here and their coefficients. But look at this. This is before our estimate of standard error. The intercept was within about 29, of income within about 0.4. They're small numbers relative to the coefficient, so they're reasonably good. 0.09 compared to 81. So, um, maybe the correct coefficient is really 65, or maybe it's 90 or 95 or something, but it's in that ballpark, so I can get estimates of these. When I refit my model, the coefficients changed a little tiny bit, very small amount of change really. But look at the standard error. It went from 29 to 16, from 0.4 to 0.2, from almost 0.1 to 0.05, from 10 to 5, from 3.3 to 1.8. That the standard errors got cut in half, which was maybe a bit of a surprise, maybe something a lot of people don't care about, but it means all of these coefficients are more accurate than those ones were. I've measured them more precisely because they've got much smaller standard errors. So my formula overall is a better formula because I can be confident that the numbers in my formula are much more accurate than I had before. So as my model improves, generally my coefficients get better. What if, though, the coefficients changed a lot, or the standard error changed a lot? That, I'm not sure if I raised that issue here. Okay. Yeah, I make mention of it here. Do I? I just want to, okay, go back, and I'm going to go way back. I'm going to go back to income limit. Okay, make this guy bigger so you can see it. And I talked about this before, but I just want to reiterate how important it is that back here at the beginning, I estimated an intercept, and I said I could easily be off by 45, maybe even 90, twice the standard error. That with rating, my guesstimate of the role of rating was 2.2. As the rating goes up 1 point, the balance I thought was going up by 2.2. But I had a lot of error in this. I could easily be off by 0.95, I said. That meant that's almost 1. So maybe the correct coefficient is as low as a little bit more than 0, maybe just 0.5. Or maybe it's as high as 4. Well, that's quite a range, 0.5 up to 4. There's a lot of wiggling there. That goes from a line that's sort of almost flat to one that's quite steep. So, but I still was saying it was increasing. That was quite clear that it's increasing, but I don't know if it's increasing slowly or increasing quickly. That's where that standard error comes in, as to how accurately can I estimate the slope. Look at this one for limit. The coefficient was small, 0.02, and the standard error was small, 0.06. But actually, the standard error was bigger than the coefficient. That's a warning light should go on right away. That this suggests that if I was to move standard error, even one standard error, up or down, then it could be as limit increased, my balance decreased by a rate of minus 0.04. Or maybe as limit increased, my balance increase at a rate of 0.08. So am I going minus 0.04 or plus 0.08? And I could even go down faster or go up faster. I don't know where it's going. I don't even know if it's just, there's nothing. And so generally, if your standard error is big compared to your coefficient, then the variable is useless. So we've been just adding variables. If I had this happen, I would use it as grounds to throw a variable out. And it is possible that a variable that looked important at one time becomes unimportant because of other stuff I've included now in my model. Now that I know all these other things, I don't need you anymore, and I throw you away. Throw you under the bus. Okay? I just needed you to get started, but now that I'm started, I don't need you anymore. So in terms of what we've learned, that we've been looking at trying to estimate credit card balances and maybe explain why some are big and some are small. So both value estimation and causal analysis we've been playing with. We did discover those with good ratings had higher balances, but we found that limits didn't give us new information, that it was the same stuff we were already using. When we added in income, that interrelationship between income and ratings both gave us information, but because of the way they're interconnected, we can't talk about one without talking about the other. You can't separate them, because if your income changes, your rating changes. That you can't separate them. That's multiclinearity. It messes up causal analysis. That it may not affect value estimation. Okay? Its obvious impact is on causal analysis. So it's something to pay attention to. In building the model, keep it simple. It's the KISS principle, that linear models are the simplest models you can have. That the slope, that coefficient, is how fast y increases as x increases. Generally, it's very easy to explain. It's very easy for other people to understand. If you have a choice between a complicated explanation and a simple one, go with the simple one. But if it isn't a straight line, you may have to introduce a curve. And I would recommend that you keep it, again, simple. And the simple ones are generally putting in x squared or maybe x cubed. Certain types of data, it's taking logarithms. Logarithms are good with financial data at times. You can only use it on positive numbers. But if you've got data that has a very long tail off to the right, logarithms will squish the tail in. And you can interpret logarithms in a model like this. It's that sort of like saying your variables are not added together but multiplied together. They compound each other, like interest compounds itself over. That's a multiplicative model with interest. That additive models generally are simpler and easier to understand. If you take logarithms, you may end up with a multiplying model. It gets messy, but they are common, especially in economic data. But very often we have to scale our numbers, like making z-scores. And many people recommend scaling all your variables. Just do it as a matter of practice. It makes it a little trickier on interpretation, but it sometimes makes things work out more smoothly. As to how many variables, well, that's a matter of, if we're adding them incrementally, when to stop. When should you quit? I'd say only add them if your model is getting better. It's not improving it. Why? If the model is good enough for you, then stop. I know you want to make it the best, but it reaches a point you're really not making further improvements and you should stop. You'll actually make things worse if you keep adding them in and they aren't helping. They just get in the way. Residual plots are one of the most useful approaches for figuring out who to add to your model or how to add it to your model, because it tells you about the new pattern you're trying to pick up. So it's learning from your mistakes is the strategy you're using. And you can plot residuals against other variables. like we plotted residual against rating, residual against income, but we also plotted residuals against gender and residuals against student status. Um, that if it's a numerical variable, you can look at correlation coefficients and use them to help judge things. But you're looking at who has the strongest pattern between your residuals and some variable. And because if it's a strong pattern, then it's going to help you explain stuff that you couldn't explain before, taking you further. As to what sequence, um, that the first time we did it with very little thought. We just said, oh, this one looks good. This one looks good. And we just threw it in. Um, Not a good strategy. I would strongly recommend that you have a strategy for adding. I recommended using residuals as your guide, but there isn't any fixed guide. I looked at numerical variables first and then looked at categorical variables. But should you do one before the other? It's up to you. There's no fixed rule. Hopefully, you'll reach the same endpoint in the end. Okay? You've just followed a different path to get there. But different people make different choices, and maybe if you take a different path, you'll end up at a different destination that's comparable. It doesn't necessarily suggest that the path you're taking, the one I was doing, will always lead you to the top. Um, it's sort of like an optimization problem that um, if you did Quant 1 and you did linear programming, the simplex method is what was used behind the scene. It goes exploring different solutions, and it always is trying to do better. And when it finds it can't do better, then it has found the best solution. That works nicely. But there are problems where if you're going up, you may reach a peak and decide, oh, I'm at the top of the mountain. But no, there's just a little dip. And if you keep on going, you'd find that you could go further up. That you might run into with regression. Generally, it's not a big deal because you're not making super complicated models. Um, that um, Some people like to put all the variables in at the start and then start throwing them out, throwing out the ones that have a big standard error relative to the size of the coefficient. And they throw out the worst ones first, and they keep throwing people off the boat until they find um, that no, throwing them out is going to make things worse. So there are different approaches people may take. As I said, should we ever delete them? Yeah. Generally, if the coefficient is smaller than 2 standard errors, throw it away. That it probably is not adding information. Oh, typo in here. Those H's. This keyboard is awful. But uh, I'm not going to dwell on deleting it. Most people go and incrementally add. And again, knowing when to stop, it's a judgment call. You're satisfied with how complicated the model is and how good the predictions are. Because it may be we can make our predictions a little bit better, but a much more complicated model, and the complexity is not worth it. But you're making a trade-off there. There are debates about how to build models. You will find many people that teach statistics don't recommend building models like I've done. They say you start out with a theory, a hypothesis in their minds about what the relationship should be, and then you go and you look at your data and see does the data support your belief. But data miners, which came up a different route out of computer science and pattern recognition, go and look and say, what does the data tell me? And they do have their processes for going and trying to verify whether or not their conclusions are correct. That they tend to try to, this fear that statisticians have that the data may mislead you because you're biased in how you approach it. You're not, you've got your own thoughts when you're building it, that your own strategy in building it, that to keep those biases out, they think it could be dangerous. So what the data miners do is they first take one chunk of data that they use to train their model. So they don't take, if I had 400 observations, maybe I'd take 300 of them and build a model. And then once I had the model, I would go and try using it on the other 100 and see how it behaves. Does it behave as well as I think it will? And that if I was biased in the way I manipulated things at the start, then that would show up when I tested it out on the 100. So it means you need a big data set to be able to have a group in reserve so you can test it out on that. But that, um, and when you test it out, you're actually going to use statistics. You're going to say, does this model fit? Does the data support this model? So we've got a process. Um, Always try to keep it simple. Try to use as few variables as you can. Try to keep the form of the formula as simple as you can. Linear is best. Um, each stage, look at the data, see what you can improve by looking particularly at the residuals. If you need to add a curve, try to keep it simple. If you've got groups of outliers, that means there's room for using a categorical variable, a qualitative variable. And we've just looked at a binary one, a 0, 1. If I was looking at ethnicity, it's a little more complicated. I don't think we need to get into it, but it's a relatively straightforward process to do that. I've hit you with a lot of stuff already, and I don't want to overwhelm you with it all. Next class, I'd like to change gears quite significantly. We're going to move to classification models. Um, that's trying to classify who is pregnant, who is not pregnant. And we're not going to get into, we've gone into the weeds with regression. We've gone quite deeply into it, far more than you would get in most stats classes, and how to build a model and those sorts of things. That in part, that's because regression is far and away the most commonly used tool for doing value estimation. That there are other methods, but it is the most common one by nothing else compares really. But with classification, there are many different approaches and new approaches coming up all the time. Some of them are very intuitive type ideas, and it reflects the way some of us make decisions. And it's worth exploring for those reasons, because if it's intuitive, then it may be easier to get buy-in of getting someone to accept your model. We'll start out saying, could we use regression to do classification? But we'll find it doesn't work well, and that we'll try to find something better than that. And after that, we'll probably be using Excel very little for quite a while. That we'll be looking more at broader concepts and ideas and less of the manual types of activities, except for probability we have to explore and do that manually. So that takes us to the end today. I hope you are still with me, and you take care. You'll see me again on Thursday. If you're trying to reach me today, as I said, I'm in Kingsburg. I have to go see my dentist though, right after class, and he's in Halifax. So I'm going to be gone most of the day traveling to Halifax and then back here again. But I will answer emails when I get back, or you can reach me tomorrow. But you take care. Yeah, are you going to get it back? I'm marking it at the moment, slowly. I've posted the solutions to assignment 2. So do read through those. Don't wait to get yours back. You've got your own and you have the solution. So you should be able to look through and get some ideas there. But you'll see that assignment 3 is completely different because it's all into regression, and they're very much different topics. But I'm slowly getting caught up on my marking. That ones that I'm marking manually on paper, I have to go and enter the stuff. I've done those. And yes, Chang, I'll send you that. And but I should be getting through them soon. They're anyway. You take care, and I'll be in touch. Bye bye.